Namaste. I am Dr. Neeraj Upadhyay, an assistant professor in Department of Chemistry, Dr. Hari Singh Gaur Vishwavidyalaya. Today, I am going to deal with you a very interesting lecture with title Color and Constitution. This lecture is written by Dr. Sumit Kumar and Dr. Rampal Pandey. Dr. Rampal Pandey is also the co-coordinator of this course. After learning this lecture, you will be able to know what is light, primary, secondary and tertiary sources of colors, complementary colors, relationship between color and constitution, chromophores and auxochromes, bathochromic and hypsochromic shifts, hyperchromic and hypsochromic effects, and modern theory of color, that is valence bond theory and molecular order theory about colors. Light is essential for the origin of the life. The primary natural source of light is sun in the solar system. There are also many artificial sources of light such as matches, candlelight, lighters, torches, lamps, lasers and many more. You all know light is an electromagnetic wave. The electromagnetic wave has both magnetic and electric component which propagate in plane perpendicular to each other and to the direction of the propagation. The wavelength of the electromagnetic radiation is defined as the distance between two identical peaks or two identical crusts. The white light defined as the combination of wavelength from 380 nanometer to 760 nanometer. A wavelength range of 605 to 750 nanometer shows the red color, while 400 to 430 nanometer wavelength range shows the blue color. Let us understand this in detail. The science of color is known as chromatics or colorimetry. There are different types of color: primary, secondary and tertiary. The primary colors are red, yellow and blue. The secondary colors are the color formed by mixing of two primary colors, and these colors are green, orange and purple. The 6 tertiary colors formed after the mixing of primary as well as secondary colors, and these colors are yellow orange, red violet, blue green and yellow green. Figure on your screen shows primary, secondary and tertiary colors. A substance looks white when combination of all the wavelengths of visible light get completely reflected back, whereas it looks black when it absorbs all the photons of visible light. If a part of band is absorbed while the rest is reflected, the substance gets the color of the reflected light. If only a single band is absorbed, the substance has the complementary color. The complementary colors are the pair of colors when combined to each other. Table on your screen shows the complementary colors of the respective color absorbed. The color wheel, as was shown earlier, helps to understand the complementary color, which is mostly directly opposite to the absorbed color. If the entire visible range of band is absorbed except a single band, the color of the substance depends upon the reflected band only. The substance looks yellow-green because the absorbed color is violet. The substance appears colorless when the entire absorption band is in infrared or ultraviolet region. Let's talk about the constituents of colors. Chromophores and auxochromes and the relationship between color and the constitution is a subject of great interest, such as the physical and chemical properties of the compounds. There is a certain relation, so benzene is colorless whereas its isomer fulvene is yellow. Some theories have been proposed to explain the observed general relationship existing between color and constitution on the basis of experimental and theoretical analysis. Let us include some historical background in this study. Owen Witt in 1876 observed that the colored compounds contain certain unsaturated groups. The group is responsible for color is called chromophore, and the compound containing chromophore is called chromogen. Some examples are keto group ethylene, nitroso, nitro, azo, quinonoid, etc. We also discussed about the group called auxochromes. The genesis of auxochrome word is from the ancient Greek word auxen, means increase, and chroma means color. When auxochromes introduced in the chromophores, it increases the ability to absorb the light, therefore deepens the color, but itself do not absorb the color. These groups can be acidic or basic. Examples of some of these groups are chloride group, bromide group, iodide group, hydroxyl group, amino group, aldehyde groups, acid groups, etc. Auxochrome is a functional group consisting atoms with at least one pair of electrons that participate in conjugation with chromophores and so deepen the absorption of light. Benzene is colorless, but nitrobenzene is pale yellow because nitro group acts as a chromophore. Para-hydroxynitrobenzene is a deep yellow colored solid due to hydroxyoxochromes. Azobenzene is colorless and does not serve as a coloring agent, but para-aminoazobenzene with amino-auxochrome is colored. Some interesting theories are also discussed to understand the connection between color and their constituents. Armstrong in 1885 proposed that all quinoid structure is coloring substance, and so it is believed that a structure of the compounds having quinoid is colored, otherwise it is colorless. Benzene and benzoquinones are examples. Benzene is colorless, whereas benzoquinone having quinoid structure is colored. Bayer in 1907 proposed the possibility of a count of tautomerism for the color of a substance. Doebner violet dye is an example. A rapid exchange between two tautomeric form occurs on a rapid transfer of chloride ion between two amino groups. Watson in 1914 suggested that the tautomerization is a major requirement for colored compounds. After the discovery of colored compounds without quinoid structure, these theories given by Watson and Armstrong are not being valid. Bury highlighted the relationship between the color of a dye and resonance. Watson proposed that triphenylmethane dye such as Doebner violet color come from oscillation of atoms, but Bury suggested that instead of movement of atoms, electrons move as increase of resonance. Further, it will be interesting to understand that the modern theory of color. During the discussion of this theory, some spectroscopic terms will be frequently used. So, let us discuss about them first. Bathochromic, made from Greek word bathis means deep and chroma means color, whereas hypsochromic, made from ancient Greek apsos means height and chroma means color. It means that a bathochromic and hypsochromic shift is a change of spectral band position in absorption spectra to the longer and shorter wavelengths respectively. Thus, the bathochromic shift deepens the color, whereas hypsochromic shift lightens the color. Bathochromic shift is also represented as red shift, as the red color in the visible spectrum is the longest wavelength. Similarly, hypsochromic shift is represented as blue shift because of the similar reason. The deepening of color of the compound means the change of color from yellow to orange to red to violet to blue to black in the complementary range of absorption color. This shows that the deeper if the majority of color absorbed has the wavelength longer than reflected color, and therefore the deeper complementary color has been absorbed. The intensity of color is determined by using Beer-Lambert's law. The quantitative estimation of intensity of color of the compound is molar extinction coefficient epsilon, which is determined by using Beer-Lambert law. According to this law, A is equal to epsilon Cl. Here A is absorbance, C is concentration, and L is the path length of light travelled in the compound. The increase or decrease of the intensity of absorption is termed as hyperchromic or hypsochromic effects. There are two approaches to understand the modern theories of color. These are valence bond and molecular orbital theories of colors. The major difference between valence bond and molecular orbital theory is that the former dealt electron in pair, whereas latter one dealt electron in single. The electron pairs in the valence bond theory act like an oscillator. As the oscillator interacts with the photon of the certain wavelength, it excites from the ground state to excited state. The wavelength of absorbed photon depends upon the energy difference between the ground state and excited state. The smaller will be the energy difference, the longer will be the wavelength of absorbed photons. An example is ethylene. There are two canonical structures, structure 1 and structure 2 of ethylene. This you can see on your screen. The neutral molecule serves as the ground state due to its low energy. The difference between the ground and excited state is very large for a small system such as ethylene, so that the wavelength of absorption of photon is too short. This is the general case of the small molecule, but it is found that for the larger conjugated system, the extended delocalization of electron, as in the first structure of resonance or canonical structure, stabilizes both ground and excited state, and so the energy difference between the ground and excited state decreases. Therefore, the wavelength of absorbed photon increases in case of larger conjugated systems. This is the general case for the small molecules, but it is found that for larger conjugated system with extended delocalization of electron, as the resonance or canonical structures stabilize both ground and excited state, so the energy difference between the ground and excited state decreases. Therefore, the wavelength of absorbed photon increase in case of larger conjugated system. The charges of the conjugated system delocalized over extended system and contribute more in the stability of the excited state than ground state. So, the energy difference between the ground and excited state further decreases. Also, the increase of number of electrons in conjugated system increases the number of resonating structures, and so increase the stability of excited state. It decreases the energy difference between ground and excited state, which is responsible for the longer wavelength of the absorbed photons. The extended system with conjugation results the smaller energy difference between ground and excited state. Thus, longer wavelength of photons absorbed. For example, the group producing either inductive or resonance effect in the conjugated system extend the conjugation and charges on it. It increases the contribution to the resonance hybrid structure, and so it stabilizes the excited state. For example, benzene is stabilized by multiple Kekulé structures, absorbs photon at 204 nanometer. The amino or nitro groups introduced the bathochromic shift in the lambda max and increases the lambda max. So, if you can see, benzene absorbs at 204 nanometer, aniline at 230 nanometer, nitrobenzene at 270 nanometer, and para-nitroaniline absorbs at 375 nanometer. Both electron withdrawing and donating group introduce the bathochromic shift to the wavelength of absorbed photon. A systemic study is shown on your screen as a table. Amino, dimethylamine, diethylamine or electron donating groups, whereas nitro is electron withdrawing group. The study shows that as the electron withdrawing or electron donating inductive effect increases, the lambda max shows the bathochromic shift from the lambda max. In the table shown on your screen represent how the change in functional groups X and Y changes the wavelength of absorption. The steric effect also have the strong impact on color of the compound. The color of the compounds depends upon the stability of ground as well as excited state. It depends upon the extent of resonance in the conjugated system. The introduction of the hindrance in the resonance in conjugated system by the steric effect largely decreases the stability of excited state and so decreases the energy difference between the ground and excited state. It induces the hypsochromic shift of lambda max. Now, let us deal with the molecular orbital approach to color. The molecular orbital theory, in contrast to valence bond theories, deals with the excitation of a single electron. The electron is excited from the occupied molecular orbital to unoccupied molecular orbitals. The bonding orbitals are at a lower energy than the anti-bonding orbitals of the molecule. So, bonding orbitals are first to fill up. You can see this on your screen as a picture. In the molecular orbital theory, the transition is an excitation of electron from sigma to sigma star bonding orbitals. Here sigma is the bonding orbital and sigma star is the anti-bonding orbital. This transition has the highest energy difference and so a small wavelength. Similarly, pi to pi star transition is an excitation of electron from pi bonding orbital to pi star anti-bonding orbital. An additional n to pi star or n to sigma star transition are possible in molecules having a lone pair of electrons. These transitions take place from non-bonding orbital to pi star anti-bonding orbital or sigma star anti-bonding orbitals respectively. N to pi star transition can be observed in molecules having double bond with lone pair of electrons. These transitions takes place from non-bonding orbital to pi star anti-bonding orbitals and to sigma star anti-bonding orbitals. N to pi star transition can be observed in molecule having double bond with lone pair of electrons such as C-O, C-N, C-S, etc. So, different amount of energy is absorbed for different kind of transitions. The order of transition on the energy difference between bonding and anti-bonding orbital you can see on your screen. These different transitions are discussed in detail. Alkane has only single bond C single bond C and C single bond H it contains, and so sigma star transition is only because of transition in case of alkane. As these transition has largest energy difference, hence the sigma to sigma star transition in ethane occur in UV region at 140 to 150 nanometer. When alkane is combined with auxochrome, sigma to sigma star transition show a shift to longer wavelength. For example, sigma to sigma star transition in RCl, RBI, RI and ROH occur in the range 170 to 175, 200 to 210, 255 to 60 nanometer and 180 to 185 nanometer respectively. This you can see on your screen. Alkanes have both single and double bonds, thus sigma to sigma star transition in addition to pi star transition is possible. For ethene, the sigma to sigma star transition takes place in far UV region, lambda max equal to 175 nanometer and epsilon equal to 5000. Here, epsilon is the molar extinction coefficient which measures how efficiently a chemical species or a compound absorbs the photon. Further, butadiene has a conjugated double bond shows pi to pi star transition in the UV region with a huge change in molar extinction coefficient, that is epsilon becomes 21,000 unit. The reason for the change in the stabilization of orbital is due to resonance in conjugated double bond system, which shift the absorption band in longer wavelength region. To understand in detail, the molecular orbital diagram of butadiene is shown here on our screen. There are 4 pi electrons in butadiene that needs 2 molecular orbital there to occupy. You can see shape of psi 1. This does not contain any nodal surface and therefore is of lowest energy. Psi 2 is the second occupied orbital but contain one nodal surface and therefore has higher energy than psi 1. Psi 3 contain 2 nodal planes and have even higher energy, and psi 4 contain 3 nodal plane and therefore has the highest energy. In terms of occupancy of electrons, psi 1 and psi 2 serves as the ground states. Psi 3 and psi 4 are the excited state. Psi 1 is the lowest energy occupied molecular orbital and psi 4 is the highest occupied energy molecular orbitals. Psi 2 and psi 3 are highest occupied molecular orbitals and lowest unoccupied molecular orbital respectively. Transition from psi 2 to psi 3 is the smallest allowed transition here. More the number of conjugated orbitals are to be occupied, less would be the energy difference between the orbitals. So, the conjugation decreases the energy difference between highest occupied molecular orbital and lowest unoccupied molecular orbital of the compound. Compounds having extended conjugation system decreases the energy difference between HOMO and LUMO and correspondingly wavelength of absorption of photon increases. As you know, energy is inversely proportional to the wavelength. In the polyene, the transition in the blue region and the polyene appears in the complementary yellow color. In the case of methanol, the two transition at 150 nanometer and 183 nanometer have been observed. The shorter wavelength 150 nanometer is due to sigma to sigma star transition. Introduction of hydroxyl auxochrome creates bathochromic shift to 185 nanometer transition to the longer wavelength. Another transition at 183 nanometer is due to N to pi star transition. For the acetaldehyde also shows transition at 180 nanometer and 290 nanometer. These are due to pi star and N to pi star transitions respectively. N to pi star transition has also been observed in range 290 to 295 nanometer for aldehyde, 270 and 280 nanometer for ketones, 200 210 nanometer for saturated carboxylic acid, 200 205 nanometer for esters and 205 to 220 nanometer for amides. Similarly, for the crotonaldehydes, the transitions are observed at 220 nanometer and 321 nanometer. Here the molar extinction coefficient for pi to pi star transition is larger than that of the N to pi star transitions. Now, let us summarize our lecture. In this module, we learned light is the electromagnetic wave where the wavelength defines the color. White light is the combination of multiple colors under wavelength range of 400 to 750 nanometer. The red color has the highest and violet has the lowest wavelength. The absorbed radiation misses out from the reflected and decides color of the substance. The complementary colors are the pair of colors when combined to each other produces gray or white shade. The relationship between color and its constituents of a compound is a matter of great interest. Witt reported that chromophores, an unsaturated species, is responsible for color. Later quinine structure in the conjugated system is also found responsible. The two approaches to explain modern theory of color are valence bond theory and molecular orbital theory. The first one deals electron in pair, whereas the latter deals electron in single. Energy difference between the ground and excited states are larger in case of small molecule, but for the larger conjugated system with extended delocalization of electron as the charge or number of electrons on the system, the stability of excited state increases more than ground state, and so increases the wavelength of the photon absorbed. Inductive, resonance, steric effect have a strong impact on color of the compound. Inductive and resonance effect produce a bathochromic shift to color, whereas steric effect produce a hypsochromic shift. The order of transition on the basis of energy difference between bonding and anti-bonding orbital is sigma to sigma star, followed by n to pi star, followed by pi to pi star, and then n to sigma star. Alkane shows only sigma to sigma star transition due to presence of single bond. Alkenes have both single as well as double bond, and so pi to pi star transition is possible in addition to sigma star. And at last, the resonance between the conjugated double bond shift pi to pi star transition in UV region for butadiene, which is in far UV region for ethylene. In the next lecture, you are going to learn about electronic spectroscopy. That too is written by Sumit Kumar and Rampal Pandey. Thank you very much for listening this lecture carefully. Thanks a lot.